Hello, welcome to CSC 7132 Operating Systems and Networking. This is Brady Chen. Now we're going to continue to talk about Module 1, the Introduction to the Operating System. Now this is Section 1.2, the Operating System Structure. Operating system is a very complex software system. So when you design the operating system, you need to design the system, organize the system, so make sure that each part of the system can function properly. So to manage the complexity of an operating system, now the designers rely on abstraction and virtualization, as we mentioned in the earlier section, to subdivide the system into multiple layers. Okay, now here's the operating system. It's a software system. Because modern operating systems is so big, so then it can perform various different functionalities. So then it's divided into various different parts. Okay, now there's one particular part. We call this kernel. Now the kernel of an operating system is the minimal set of functions necessary to manage the system resources safely and efficiently. Okay, so there are many functions. The operating system could perform many functionalities. Now, you need to actually define some of the functions that are very critical to the system. Now, for example, one of the functions for the operating system is to manage the computer memory. So if you have multiple programs running in the computer system, now the operating system needs to manage which programs is stored in which part of the memory. And also, if you actually execute the program, now you want to make sure you're going to actually execute the instructions command stored in the memory. Okay, and then some of the instruction may ask you to, change the value, change the data stored in certain part of the memory. Okay. Now, that is very critical functions, because you don't want one of the user of one program to update the data stored by another program, right? That's a security issue. So you have to make sure these kind of operation has to be in the right hand. Okay, you don't want any other users to control this operation. Now, there's another functionality like running some kind of app, like a computer game. Now, this kind of functions have relatively low priority. So the kernel basically contains the minimal set of functions necessary to manage the system resources. Okay, memory is the system resources. CPU is the system resources. So when you actually schedule the CPU time for different programs, that kind of functions should be part of the kernel. Also, now to deal with the issues of the security of the operating system. Now the computer instructions, instructions are divided into two different sets. Okay, so the instruction set provided by the CPU is divided into privileged and non-privileged. Okay, so when a program wants to run a particular function, so the program actually send contains the instruction. So the CPU going to fetch these instructions to perform the operation. Okay, so then some of the instructions are privileged and some are not. A privileged instruction performs critical operation. Keep that in mind. A privileged instruction performs a critical operation that the access I/O devices and the CPU's status and the control the registers. Now registers are the storage in the CPU and other devices. So these are the storage in the CPU and other devices. So if the instruction gonna actually request for, updated values in the registers, then in this case only this instruction will be defined as a privileged instructions. So if it's a privileged instructions, then only the operating system kernel is allowed to execute them. That's privileged. Non-privileged is actually instructions are not relatively, less important. Mostly these are the user instructions. For example, I want to send a message out or doing something else. If these actual instructions not used to control the computer I/Os and any actually critical part of the computer system. Okay, to guarantee that no programs outside the trusted kernel can use the privileged instructions, the CPU operates in two different modes. One is the kernel mode. The other one is user mode. Okay. Now the operating system needs to want to make sure that the privileged instruction should be in the hand of good guy, and the non-privileged instructions should be okay. So if a bad guy want to mess up something that use the if it's non-privileged instructions, it's only impact the program itself. It's not going to impact the other programs. Okay. Now, for example, if you want to add two numbers, that's probably not a privileged instructions. If you want to read the system time, that should be okay. This is not going to cause any harm to the other programs or any other part of the system. So now the kernel mode, in the kernel mode, that then both privileged and non-privileged instructions may be used. So that means if the program is running in kernel mode, that means it has the highest priority. Now the user mode, if the program is running in user mode, only the non-privileged instructions may be used. So if you want to, a program wants to access a memory location doing the memory address mapping, so then you need to request for switching the mode from user mode to kernel mode. Then you can perform all these privileged instructions. Okay, let's take a look at this diagram. So all software comprising a computer system can be divided into several levels of abstraction. You have a kernel, and then the system library, system call library and general libraries. And then here's the hardware. Okay. Now, the kernel is the lowest. The kernel is the lowest level of software. Below the kernel level is hardware. And the kernel provides the basic functionalities necessary for efficiently or safely executing programs. Okay, kernel is the key. Then the kernel is extended to extended by library functions, which invokes kernel functions and to offer more convenient service functions to higher level software. So above the kernel level, there's a system call library and other library functions. Okay, provides additional abstraction to carry out some more general functionality like mathematical functions, like string manipulations, like concatenation of the strings, and doing all these manipulations at the high level. And then at the very top is the application and the system software. Okay. Now, software at all levels executing the instruction, CPU instructions. So the application and system software can directly, execute the instructions, CPU instructions. And then the general library level can also execute the CPU instructions. Okay, all levels can execute the CPU instructions. However, only the kernel is allowed to execute the privileged instructions. Okay, and then the other level can only execute the non-privileged instructions. Actually, kernel can execute both privileged and the non-privileged, but the other levels can only execute the non-privileged instruction. If you really want to actually perform some privileged instruction, like you want to change the registers, and you want to actually set up the timer, then you have to make a system call, make a request to the operating system kernel to make such a request. Okay. Next, when a user logs in, the operating system starts the user interface. This is also called a share. Now, share, remember in the previous slide, we just mentioned the different levels for the operating system. The top one is the application and the system software. And then the next level is the library, right? And also what is called a system call library. Okay. So library. Now the share is somewhere over here, right? Pretty much at the same level as the application and system software. It's actually the user interface. Now there are two, so when a user actually try to use the computer system, try to operate using the operating system, the first thing you're going to see is the share. Okay, so the share basically hide all the details of these various different functionalities of the computer operating system, as well as the hardware. So there are two types of share. One is the graphical user interface. Okay. Now the other one is the OS share. Sometimes it's called command line interface. Now the modern computer systems use more and more the graphical user interface, and many times we call it GUI. The GUI presents various icons on the screen, which the user can click on the different ways to invoke the service associated with the icons. So you can use the mouse, and you can use some kind of pointing devices to perform the operation. Now the command line interface, or OS share, is the command interpret that accepts and interprets the textual commands issued by the user via the keyboard. So the user can actually type the command. Okay. Microsoft, the early version of Microsoft operating system is called Microsoft DOS, MS-DOS. That was more than 20 years ago. So DOS basically stands for a disk operating system. Okay, so the DOS use the command line interface. Now there's various different reasons why people use the command line user interface. The earlier computer system used the command line user interface. It's because the computer screen is not really that advanced, so they don't have a very high resolution actually computer monitor, and the computer CPU is less powerful, and there's no enough computer actually memories. So that's why the command line user interface took less resources to operate. Now if you use the graphical user interface, then you're going to show all the very interesting icons and some kind of graphics on the screen. So it takes more actually memory space to store each of the images. So the share is basically, as I say, it's the interface to the computer system. Okay, let's take a look at the example of the share command in Microsoft Windows operating system. Sometimes this is also called MS-DOS. So this is the command line user interface. So basically what you're going to do is you can open a command line windows in the Microsoft Windows operating system. Then you can move to the directory or any folder, and then you can type dir, which is the command you can use to display a list of files and the subdirectories in a directory, or sometimes we call it folder. If you want to copy a file from one directory to the other, you can use the copy command, and the del, it's a delete command, and wc basically used to count the number of words, lines, and the characters in the text file. Now depend on the parameters you're going to use after the command. Okay, so that's Windows DOS command line interface. As we mentioned that more and more people start to use the GUI interface. So the main advantage of a GUI is the initiative visual representation of objects. Instead of use the command line, type the command, you basically you are able to manipulate object and invoke operations using a mouse or any pointing devices without much training and without any knowledge of the underlying commands. So a very important, very useful example is like your smartphone. So you can pretty much make a phone call by just press the one of the icon the represent the phone. Then you can actually place the phone call. And if you want to actually play some of the apps, you just press that particular app, the icon. So basically, the good thing about the GUI is you don't need any training. So it's very straightforward. So that's a good thing. Okay. So a share is the preferred interface by programmers. Okay. So when you use the share, you need to type the command. So now, because share use less resources, it's faster. Okay, it's text-based. So it's faster and more flexible than icons. Okay, and also in certain cases, like if you are an IT administrator and you want to control the server, which is actually housed in the office, and sometimes you don't have to go to the server rooms to perform the operation. You can actually control the servers remotely from your home. Now, in that case, the share command is the most efficient way if you're familiar with all the command, because it using the graphic user interface, you can actually send a huge image files, a whole bunch of image files. But the share command only use, texture command. So it's just a very small message and sent to the computer server to control the computer. It's faster. The performance is much better. So that's why the GUI user interface are widely used by people who don't know anything about the computer system. But the shell command is widely used by professionals. Now, let's take a look at the diagram again. We actually showed this just a couple of slides before. So we know that the system calls and the general libraries are located in certain level in the operating system hierarchical structure. Okay, now, so a system call is a request from an application for an OS services. Okay, a system call is implemented as a library function. So that's, many operating system implements a lot of system calls for different purposes. So it's implemented as a library function which sets up necessary parameters for the requested operation and issue and corresponding supervisor call. Okay. Now, supervisor call is actually at the lower level than system call. It's a kernel call. So if the system call request for a privileged instruction, it's going to go through the supervisor call that automatically transfer the execution control to well-detained location within the operating system kernel. So once the supervisor call is triggered, then it is automatically transferred to the kernel mode. Sometimes that's why it's called a kernel call. So that's the supervisor calls provide the interface between the OS kernel and the high-level software. So if you want to make any privileged instructions, okay, if you want to execute the privileged instructions, you have to go through the system call and trigger the supervisor call, and then the supervisor call gonna eventually, then go down and trigger the operations under the lower level or the hardware. Now we mentioned that typically users at the application level or system software level make a system calls. to trigger any kind of operations in a computer system. And now, system call is going to actually then trigger the supervisor call if the call going to actually involve in the operations on the I/O and any actually computer hardware. So now a supervisor call is similar to function call with two special features. The first one, the call switch execution from user mode to kernel mode. So that means once the system call triggers the supervisor call, the control is going to be on the kernel side. So the user lost control of this operation. And then also, the supervisor call going to hide the details, to prevent the call from breaching to arbitrary allocations within the kernel. The function to be invoked is not specified by an address. It's not going to tell, okay, please update the data in a specific memory location. The system call never going to specify the address. But it would indirectly use the index into a branch vector. Okay, we can actually illustrate this with a diagram. So let's say the user, an application running in the user mode, try to execute a system call. Say, here's the application. Okay. Okay. So you're going to execute certain of the instructions in one particular place. You're going to trigger a system call. This is a system call. So this is actually running in the user mode. So you're going to actually send by the CPU the instruction sent by CPU, and which is in the mode bit is user mode. Okay, that means it's this application is running non-privileged instructions. Now, this is going to trigger the system call. Okay, this is going to trigger the system call. Now, the system call will basically set up a parameter. Set up parameters. Okay, and then it will trigger the supervisor call. Supervisor call. Now, the supervisor call, for example, you're going to use the index k. Say, that's a supervisor call 3, supervisor call 1, to supervisor call 2. Now, in this particular case, I'm going to trigger the supervisor call k. So then, down in the kernel, and you're going to see, so that's an index. Now, in the kernel, there's a table which contains a list of indexes. So index 0, index 1, and then in one particular place, there's index k. Okay, So each actually place stores the index. Now, because this system call is going to trigger the supervisor call k, so this k going to basically point to the index k here, and this index going to actually has a pointer. Then you're going to actually point to the kernel function. Kernel function for that particular supervisor call k. Okay. Now, if the case, case 0, 1, 2, 3, 4. Now each is going to point to a certain memory location. Each index points to a certain memory location, which basically increment the supervisor call corresponding to that index. So that's the call 0. That's the call 1. So it's an implementation. So that's why in the system calls, you only see the index. You actually don't see any memory locations. So now, while this system call actually execution basically transfer to library function S. So then you're going to actually move this down. Okay, so it's still user mode. In here, this is still user mode. Okay, now when you actually trigger the supervisor call K, then this is going to actually eventually, the call going to transfer to this location. Okay, now when supervisor call is triggered, then the mode is going to be transferred to kernel mode. Okay, so it's going to be transferred to kernel mode. Now, once the job is done, you're going to return back to the system call, and then eventually return back to the application. This is how the system calls and the supervisor calls actually works. Okay, let's switch to the new topics, interrupts and traps. Let's first talk about interrupt. An interrupt is an event in which the CPU alters the execution sequence. Okay, now it's an event that diverts the current execution of a program to a predefined location in the kernel in order to respond to an event. Now, what does that mean? So suppose here we have a program running. So let's say this is a memory. So the program, in order for the program to run, you need to load the program into the memory as a whole bunch of instructions. Okay, and then here is the CPU. Now CPU and memories are connected through high-speed connection. Okay. So when the program is running, so CPU gonna actually basically fetch the instructions for the program. Okay, that's the first operation. And then the instruction is actually copied to the register. It's called the instruction register inside the CPU. It's a storage. It's a register called the instruction register. And then the CPU can actually decode the instruction. That's basically happens inside the CPU. And then execute the instruction. Okay, so this is actually a complete cycle of operation. So fetch, decode, execute. Okay, and then once it's done, CPU gonna actually fetch the next instructions based on predefined sequence. Now that sequence basically are determined during the compiler time when you actually load the programs, when you compile the program and create the executable. Okay, so it's predefined. Now interrupt happens. When interrupt happens, so a CPU will receive a signal from a device. So all these devices like a memory, CPU, and the other devices are connected through the system bus, right? So a device may send a signal to the CPU, say, hey, please stop whatever you are doing and process my request. That's an interrupt. Now, interrupt actually happens, then CPU stop its current execution and process the interrupt. Once the CPU complete the operation for the interrupt, CPU gonna be back to the previous sequence of operation. Okay. So the two most common uses for interrupt are, one is signal to the operating system the completion of I/O operations, and the other one is widely used in the time sharing. When the CPU switch back and forth between among all the programs. Remember, in the time multi-programming environment, so for the time sharing, that the CPU gonna actually switch back and forth among these different programs. Now, who's gonna tell the CPU to switch? Okay, it's a timer. So then, how the timer gonna actually inform the CPU, say, hey, it's time to stop whatever you're doing for this program and switch to the next program. It's gonna go through the interrupt. So the timer gonna send an interrupt to the CPU, say, hey, it's a time for you to switch. So that's basically interrupt. Now, trap is very, very similar to interrupt, but a trap is triggered by computer software, not by hardware, not by I/O devices. So one of the example is when you run the program doing some math problem, and suddenly you experience the situation, you're in trouble because you actually end up with, division, well, that a number is divided by 0. So then that's an error, right? So the program cannot continue. So then it will generate a trap. So we can actually illustrate these interrupts through an example. Okay, to illustrate how interrupt works, let's take a look at the example. We will actually follow the previous example of the system calls and the supervisor calls. So let's say we have application. If you go back to the previous slide, you will see, if suppose I have an application, I call this application 1. It's a user application, a program. You can interpret this as program 1. Okay. Now, the program 1 actually has a whole bunch of instructions, and in certain place, you're going to make a system call. Okay. That's a system call. Okay. The system call eventually going to actually switch to the function system call, and the system call going to trigger the supervisor call. K, right? I just exactly follow the previous example. So in this case, so initially the CPU is executing the instructions for this application. Okay, now it's actually in the user mode, right? I call the mode bit. So that's one of the bit in the instruction, just indicate whether the current instruction is in user mode or kernel mode. It's pretty simple. It's just one bit because, for example, 0 means user mode, 1 means kernel mode. And then the CPU is going to switch to the supervisor call. Okay. So still user mode. And then the supervisor call going to actually trigger the, index. So that K is the index. So basically shows, okay, that's a K. So which point to a particular place that actually implement this particular call, right? So that's what it is. Now, during this time, the CPU is pointed here, then the CPU is pointed here. Now the CPU is currently running the kernel mode. Now, this program, suppose that program is process the I/O operation. Okay, so let's say you're gonna actually send a request to the input and output devices. Okay, so then the CPU actually, the program is actually dealing with the I/O. So at this time, the CPU is no longer in use because the program going to be focused on I/O operation. The I/O operation going to be operated, on the I/O device, like a printing or scanner, or you're going to do whatever other job, or for example, waiting for the message from the internet if it's a internet port. So now during the I/O operation, the application going to block itself. So that means the CPU cannot, when the CPU is currently stuck in the system call, the system call going to trigger the I/O operation. So then the CPU cannot fetch the next instruction. CPU cannot do that because this application, this program, blocked itself. So then what we're going to do is, using the interrupt, then CPU is not going to actually idle because CPU is going to do something else. You don't want to waste CPU time, right? So then another program I call the application 2 going to be coming. So the CPU start to execute the instructions for another program. Now, once the I/O device completes its job, this I/O device is going to send an interrupt to the CPU, say, hey, I'm done my job. And then the CPU is going to move back and continue its work. And continue its work. Okay. So then, after actually system call is done, complete, then CPU going to start the next instruction in application 1. Okay. So during that time, once I/O is done, the CPU probably going to actually, perform another supervised call. Just tell the CPU to complete the I/O. So the complete I/O operation may be, going to execute another piece of code. But anyway, the CPU going to be actually back and complete the job. And then if they actually, this application, make another system call to perform the I/O job, and then when the I/O is actually working on its operation, and the CPU can actually go back to this application. So the interrupt is going to be playing a very important role in here, because when CPU actually switch away from the current actual programs, so CPU going to be back, because after the current program complete the I/O job, the I/O going to, send a signal to the CPU, say, hi, I'm done my job. So please finish up. Okay. Okay, so let's illustrate the interrupt with an example. So let's take a look at the example we just talked about minutes ago. So let's say we have an application. Okay, running. So there's a whole bunch of instructions, and one of the instructions going to trigger the system call, right? So here's a CPU running in the user mode. Okay. So CPU going to basically fetch the instruction, execute an instruction, or actually decode the instruction and execute the instruction. And the CPU going to fetch the next instruction, decode the next instruction, and execute the next instruction. CPU going to actually follow this cycle to perform its operation. And then when CPU fetch the instruction that perform the system call and decode it and find that it's a system call, and then the library function, SK, invokes the corresponding supervisor call. Okay, it's a kernel function that they're using the supervisor call. Remember, the supervisor call use the index, right? So index K. Okay. So then the supervisor call going to switch the CPU to the kernel mode in the kernel area. So then this is a table just which contains a whole bunch of index. Okay. Now the supervisor call K going to lead the kernel call to this index K, and then it will start an IO operation. So the CPU going to actually start to execute in the kernel mode, start the IO operation. So you're going to actually start the IO. Okay. So now then it will ask the IO device to transfer the data, for example. Now if the data transfer going to take a long time, so mostly it happens in the IO device. So IO going to actually perform the data transfer, and then the CPU going to actually the application 1 will be blocked because the IO operation going to take a longer time. So it will be stuck in this instruction. So the CPU is not going to go to the next instruction, fetch the next instruction, and continue the application 1 because it's blocked. It's blocked here. So in that case, the CPU is going to be idle, right? So nothing else to do. So in this case, the kernel going to select another application to run, while application 1 is waiting for IO device to complete the data transfer. Okay, so CPU gonna the kernel gonna pick another application. I call the application 2. Okay, so the application 2, so the CPU gonna start to execute the instructions in application 2. So let's say CPU fetch the instruction, decode the instruction, and execute the instruction, and just continue. Okay, now suddenly, when CPU complete the instruction I, then the IO device over here, remember the IO device at the very bottom, complete the data transfer. So the IO device is going to actually send a signal, actually send an interrupt to the CPU, say, hey, I'm just done my job. Okay, so once the CPU receive the interrupt, okay, once the CPU receive the interrupt, CPU gonna actually switch back to the kernel function. Okay, so when the data transfer complete, the device issue an interrupt to the CPU, then it's gonna stop. The CPU gonna stop the application 2. It's gonna stop here. Stop the application 2. Okay, so then, after, then using the same branch vector, it's just check the same branch vector, and as a supervisor call the kernel transfer control to another function. Okay, so it just say, okay, I stopped the data is completed transfer. So another actually, so the kernel function gonna actually use the same index table. So now this time it's not a k, it's probably m, send another index, and the other index basically actually gonna stop the just say IO operation is stopped. Okay, so this m index, it's another supervisor call that was complete the IO operation. Okay, so it says IO completion. So it's another call. Okay. So the IO completion routine gonna basically, once it is finished, it will move back. The CPU gonna move back to the system call. Okay, and then it will move back to the original system call, complete this job. So then the CPU is supposed to execute the next instruction in application 1. Okay, so now if the application 1 make a system call again somewhere, like a S system call again here, and then the whole thing start over again. Okay, so it will trigger the kernel call using the system supervisor call K, maybe still the data transfer, it's gonna call the K again. So you're gonna actually make an IO operation, and so you're gonna repeat the same processes. This is how the interrupter works. Okay, so interrupter is done through something called the interrupt handler. It's a kernel function. So it's invoked whenever an interrupt occurs. Okay, so the interrupt handler determines the cause of the interrupt and invoke the appropriate kernel function to provide the response. Okay, depend on the type of interrupt. Okay, so interrupt coming from different devices, and different devices may request for different operation. So the interrupt handler gonna determine what kind of operation the interrupter gonna take to perform this job. Okay. Thank you.